Swayam Prabha. Digital India. Educated India.
This maritime engineering, as you see, is a very special program which has got multidisciplinary input from mechanical, civil, structural, aerospace, naval architecture, chemical engineering, electrical, electronics, applied mechanics. It's a multidisciplinary program. You will find this program is completely different, dedicated to industrial training and thorough capacity building on the new trade of maritime sector. It's a grooming economy which will give you a lot of job opportunities and research frontiers as far as India is growing. And the Blue Corridor effect, which is planned by Government of India, is one of the important mission which requires maritime engineering growth to happen in the country. So this program caters to expected that capacity building in this program.
Friends, this is part of a material science engineering laboratory which becomes one of the teaching aid for the maritime engineering program. So when you talk about materials innovation in maritime industry, though concrete and steel have been conventional candidates of choice for engineers, for example, we have titanium vessels, high-speed craft boats made of fiberglass. These are all advanced materials which actually do not come across conventional standard design code of practices. We conduct box furnace test, tube furnace test, vacuum arc melting, induction melting, vacuum induction melting, vacuum sealing unit, which are all present in this laboratory is a small segment of material science laboratory. Friends, a typical furnace where the operating temperature for testing specimen can go as high as 12 degrees Celsius. Generally at room temperatures and ambient condition, the mechanical properties will not alter much. As you see in the course lectures, you will notice that strength of the material get degraded when the temperature rises beyond 600. Therefore, when you talk about fire resistant design, you must also choose an alloying element such a manner that the strength doesn't degrade beyond 600 degrees Celsius at all. Welcome to the ambience of IIT Gandhinagar lecture theatre. This is one of the interesting classrooms where the maritime engineering classes will be conducted. We have got state-of-the-art projection facility and good audio-visual recording systems. Once the lecture is over, you see the system here. We can generate the PDF files of the lecture directly and you can email the PDF files directly to your email IDs. So it's a state-of-the-art facility we have in IIT Gandhinagar where the lectures are lifetime recorded and shared with the students immediately. This is the IIT Gandhinagar library. This has got all collections of books which are referred as the standard textbooks and references for the course and the program. It also has lot of online editions of design code of practices and reference materials and e-collections of various video lectures of international courses and programs related to maritime engineering. We will be taking you around to the advanced material manufacturing units. So you will have state-of-the-art facilities available at IIT Gandhinagar. So welcome to the program to join MTech and PhD at IIT Gandhinagar Maritime Engineering. So please try to enjoy and take the advantage of this to the maximum. Welcome to the program and welcome to IIT Gandhinagar. Welcome friends, we will continue with the class on maritime structures. Welcome to this lecture 24 where we are going to discuss about extended aspects of fire resistant design as applicable to structures under hydrocarbon fire. We have already seen in the last two lectures how fire can be classified as per the international codes of provision based on the material for combustion and of course based on the type of fuel which has been done, and we have also seen how fire system can be put in place to mitigate fire, to control the spread of fire, and what are the different systems of fire fighting which are normally deployed in heavy industrial structures including offshore maritime structures. So in this lecture we will give you a flavor how to do quickly a fire resistant design using a software which will be done by my colleague Dr. Pratibha. who specializes in fire structural engineering. So, this teamwork is a joint presentation by me and Dr. Pratibha, who has done extensive work on fire resistant design under hydrocarbon fire. Prior to entering the numerical modeling and fire resistant design of structures under hydrocarbon fire, we will talk about some basic inputs which are required and to be understood before we do this kind of design. So, of course, in another special course, we also talk about detailed methods and steps involved in fire resistant design step by step. However, in this course, as a primitive understanding, we will give you a lecture on how a fire resistant design can be quickly learnt for offshore maritime structures. So, friends, as we understand, the properties of materials under elevated temperature significantly changes, and these properties with respect to time and temperature need to be added and upgraded in the input of the software to take care of the correct value of strength and stiffness of the members and material respectively when we model them in the software. So, as the temperature rises from ambient condition to any other higher order because of presence of fuel based fire, naturally it degrades the strength of materials. Steel is no exemption. So, when we talk about design consideration for steel at elevated temperature, then look at this curve which shows me the modulus of elasticity or Young's modulus of steel. The reduction happens in Young's modulus of steel with temperature rise. So, the reduction factor varies beyond about let us say 170 degrees Celsius, and the Young's modulus degrades significantly, and practically it comes to 0 at 1200. It means the steel does not provide or possess any elastic property at all at higher temperatures. It becomes like a flowable material, right. So, now this reduction factor is essentially to be modeled as an important input component when you use steel as a construction material for designing the system under elevated temperature. So, we already seen from this figure that the modulus of elasticity decreases with the increase in temperature as you see in the curve here. It implies that there is a reduction of stiffness which leads to large deformation under the same load. That is an important aspect in the design here. We are talking about a member or a structural system which experiences large deformations under the same load without an increase in load, because there is a degradation of Young's modulus with the increase in temperature. So, as far as design consideration is concerned, this should be incorporated as a reduced stiffness caused by excessive deflection, and therefore, when we perform dynamic analysis or vibration analysis of structures, this should become an important input as the material is exposed to higher temperature in case of fire. So, there is a degradation of modulus of elasticity which is imposed as a reduction factor with the increase in temperature that need to be modeled as an input in the software. Secondly, look at the yield strength of steel. So, this curve shows me how the yield strength reduction takes place with the increase in temperature. So, you know, till 400 practically there is no reduction in yield strength, but after 400 there is a significant reduction within about let us say 250 degree extra from 400, the strength falls 90%. Okay. So, yield strength practically comes to negligible amount when you have a temperature about 650-700 degrees Celsius, whereas hydrocarbon fire reaches temperature about 1100 degrees Celsius. Okay. Practically yield strength is 0 for the material there. So, the yield strength starts decreasing significantly after 400 degrees Celsius, at 2% strain. So, it has got two consequences: yield strength decreases, strain becomes completely flowable. I mean, it becomes very large deformation systems. So, the implication in this property in design could be the structural components may fail to carry the design load at elevated temperatures, because yield strength does not give you any value beyond certain temperature. Therefore, in design consideration, temperature dependent yield strength should be incorporated, so that the load bearing capacity of the member should be estimated based on this revised properties. Okay, that is an important input again. One input is reduction in modulus of elasticity, second input is reduction in yield strength. Furthermore, as far as ductility is concerned, ductility increases the temperature, because there is a flowable property, it allowing larger deformation before failure. The implication should be, while deformation capacity improves, the structural integrity and safety margin reduces. Therefore, one should ensure connections and joints to accommodate this kind of excessive deformation or large ductility when steel is exposed to higher temperature. The thermal expansion occurs as the temperature rises, leading to elongation of members. This can induce thermal stresses in the constrained systems or misalignment of the structures, what we call as lack of fit. This is a very serious problem when you have got multi-span 3-dimensional space stresses, which are also used as deck support systems in offshore structures. So, you have got lack of fit arising because of misalignment of the structure as a result of high temperature. Therefore, this should be accounted for thermal expansion coefficients in the design and so on. If you look at the thermal conductivity and specific heat, thermal conductivity with respect to temperature and specific heat of steel with respect to temperature, one can say that specific heat of steel significantly increases and drops suddenly at a specific shoot up temperature. Okay. So, if you look at the thermal conductivity, it changes the temperature, affecting heat transfer within the material. Specific heat actually influences the rate of temperature rise in steel members. It implies that these variations in property of steel affects temperature distribution and rate of heating in steel. Therefore, one should use fire insulation materials or coatings to control temperature rise and ensure uniform heat distribution in the design. If you also look at the plasticity properties of steel at elevated temperature, steel becomes more plastic at higher temperatures. Therefore, it reduces its proportional limit. Structures therefore may exhibit permanent deformation before failure. Therefore, one should perform inelastic analysis for critical members to evaluate plastic deformation limits when steel is under high temperature. The specific weight of steel remains almost constant, but should be factored when designing for thermal effects. One must ensure that the temperature induced distortions or deformations do not lead to instability due to self weight. That is very important aspect as far as steel is concerned at elevated temperature. Now, let us talk about the key properties to define in fire resistant design. One should include reduced modulus of elasticity, reduced yield strength as a function of temperature, and we also know temperature now is a function of time as well. Okay? We have already seen the TT curve yesterday, the standard fire curve and the design fire curve yesterday. So, temperature dependent thermal conductivity, specific heat and thermal expansion coefficients should be a part of the input system in the design. Fire design standards such as Eurocode 3 Part 1-2 or IS 800 with fire specific provisions are also be followed in this situation. Let us talk about structural stability under fire load. The important challenge of stability under fire load is, as we just now saw, the system exhibits or experiences large deformation, okay, at elevated temperature. These large deformations, apart from causing lack of fit and causes geometric instability, can also induce thermal buckling and lateral torsional buckling. Friends, in the previous lectures, we discussed about the consequences of LTB because of large span and deep web conditions. It also can be invoked under high temperature. Therefore, one should perform stability analysis at higher temperatures considering reduced strength and stiffness of material. If we talk about fire protection systems and their influence at elevated temperature, active systems like sprinklers, water sprays, passive systems like fireproof coatings, insulation materials cause passive and active fire protection to the steel structures, and they should be designed in such a manner that the integrity of the structure during exposure of fire should be maintained. So, it is not that the geometric stability alone is important, the whole structural integrity must be maintained and the system should remain functional, not for occupancy, but it should not lead to complete collapse. Therefore, friends, the best way of doing fire resistant analysis and design is a detailed finite element model incorporating all these changes as property of material. Therefore, one should suppose to use advanced analysis tools to simulate thermal stresses, plastic behavior and failure modes at elevated temperature. It is necessary that we incorporate temperature dependent material properties in the simulations at every time interval during simulations, because you know the variation of the thermal characteristics of materials are time dependent, therefore, and they are nonlinear as well. So, one should also think of including the temperature dependent material properties with respect to time as well when you perform dynamic analysis. So, now when we come to the fire resistant design part of the system, in simple terms, if I have a load resistance R of a member, we already understood that the load resistance of the structural member usually decreases with the increase in temperature, and the reasons could be there is a strength and stiffness degradation in the material strength. Therefore, friends, in general philosophy of design, this resistance should be more than the demand raised by the fire load. Now, one may ask me a question, how to compute the demand raised by the fire load? We already saw a glimpse in the previous lecture how to compute the flex and HRR for a standard fire curve. If I have the material in place and each material has got its own calorific value, can always compute the thermal load or the fire load. And if I can compute the fire demand raised at high temperature, the resistance of the system should exceed the demand raised by under fire loads, which is a very general dynamic philosophy. There is no change in this. The time at which this equality holds is become important. You know, the demand as well as resistance keeps on changing with time. That is an important factor here. Though this equation looks like static, but it has got a dynamic variation, because even the fire load as well as the resistance of structure under fire or elevated temperature both significantly varies with time. Therefore, at any instant of time, the equality of this should be assessed based on what we call fire rating. Therefore, friends, fire resistant design is not a process where you make the system fire resistant. You only make the system fire proof for a specific time, what we call as fire rating. So, typically fire rating of structures are expressed in hours or minutes. So, if I say the system can sustain fire rating up to 30 minutes, it means till 30 minutes the system does not collapse. Okay? So, the fire rating is to be established and the fire rating comes into picture here because the properties of resistance and load demand from fire keeps on changing significantly with time. Now, let us ask a question, how this design is different from design done under ambient temperature. When we compare the design under normal temperature, design under fire scenario typically entails larger amount of applied loads, lower amount of applied loads, possibility of additional internal forces or displacements arising because of thermal expansion, reduction in strength of material, reduction in cross sectional area due to spalling in case of concrete, etc., and possibility of different failure mechanisms. For example, there can be a location of local plastic hinge because of excessive stress concentration caused by strength degradation. So, all these factors will lead to make the fire resistant design different from that design done under ambient temperature. So, let us talk about fire rating, because in dynamic analysis, when the time is an implementing factor for both resistance and load, then fire rating plays an important role. A fire resistance rating is the duration for which a passive fire protection system can withstand a standard fire resistance test. This can't be quantified as a measure of time. For example, if you say 1 hour of fire rating, then it consists of various building material that can resist the exposure of fire, standard fire for 1 hour. Okay? Now, there are 3 different criteria. One is load bearing criteria, other is integrity criteria, third is insulation criteria. Load bearing criteria is what we call the system should resist the load under fire. The system should resist the load as well as remain integral. The integrity is also maintained under fire. We call this RE category, and the insulation material does not allow fire to propagate and increase the rise in temperature. Therefore, we call this REI category. So, there are 3 divisions of design, what we call only resistance or load bearing capacity, load bearing and integrity conditions, and load bearing, integrity and insulation criteria. So, there are 3 different criteria based on which a fire resistant design is done. Let us look at what are the codes of practice we have for fire. There are handbooks available based on experimental investigation, smoke control and management, and engineering data which are used for fire models. There are different standards available for general rules for buildings, fire design for different structures like fire design for steel, fire design for concrete, fire design for composites. There are different books and literature available. Fire and life safety are integrated by design codes. To estimate the calorific value in the material property, we can also assess tests of materials under fire with ASTM standards. Then we also have fire detection and fire protection equipments in place in the market, which can be used readily for firefighting and suppression systems in fire. ISO 834 fire resistant test, a standard procedure which are used to compute the fire resistance for elements of building construction. Eurocode 1992 part 1 to 2004 is used for design of concrete structures. 1993-2005 used for steel structures. IS 3809 is used for fire resistant tests for structures. National Building Code of India, the revised one part 4, also talks about fire and life safety. ASTM E119 helps you to establish standard test methods for fire. DNVGL offshore structures 3301 offshore standards also help you to understand the fire protection systems in place for maritime offshore structures. British standards 9999 2017 also helps us to learn and understand fire safety in design, management, use of buildings, the codes of practice. So, various codes of practice in the international scenario are available for fire resistant design, friends. So, if you look at the design consideration very quickly, for tension members, the axial force under fire should be based upon this equation, where Fy is the normal temperature yield strength not reduced strength of the material, and A fire is the area of cross section which is exposed to fire. Usually this area of cross section is for cold steel sections, but this area now allows the consideration of scenarios where cross section area may reduce during the fire event. For example, if you have got a bulk concrete column where under fire the cover falls off, we are talking about area resisting fire is the core area. Okay. Therefore, the axial force or axial tension under cold condition is Fy of area. One may view the capacity under fire conditions as Kyt of cold. It means there is a factor multiplied, to understand the axial force or tensile force required for design under fire. Please note that there will be situations when the bolted connections are used where the material stress other than yield strength will be required. Okay? For example, in case of connections, the methodology however will not change and the corresponding strength reduction factor can be used in a similar manner. If we talk about design for beams under flexure, then beams with lateral torsional buckling is not critical. The moment carrying capacity is given by the factor multiplied by the capacity under cold condition to obtain the capacity under fire conditions. Whereas M cold is a normal temperature moment carrying capacity, the elastic lateral torsional buckling moment which we computed in the last lecture for under cold condition, but changed under fire condition is given by this equation, whereas the critical buckling stress at elevated temperature is given by this value divided by Zp, where Zp the plastic section modulus of the section. Then as we know, the slenderness ratio plays an important role. A non-dimensional slenderness ratio under fire condition is given by this equation, whereas the bending stress reduction factor for LTB at an elevated temperature is given by this equation. Therefore, friends, by knowing this I can always compute Zp is known to me, psi LT is known to me, and Kyfy is a function of this which can be computed. I can compute the moment carrying capacity of the member at high temperatures. Now friends, we will demonstrate now the numerical analysis for fire loads. We will take an example of a simple structural system. We will use a software. We will try to demonstrate step by step how this can be helpful to do analysis under fire loads. Dr. Pradima will demonstrate this lecture using a software. Thanks to the PyroSim academic license, which is now going to be helpful for a tool or a learning medium for people listening to this course. Over to Dr. Pradima.
Hello friends, welcome to this lecture on fire resistant analysis and design. In today's session, we will explore the principles behind designing structures to withstand fire. And it is a critical aspect of safety in engineering. Fire resistance is a key factor to ensure that buildings, particularly steel structures, maintain their structural integrity during extreme heat exposure. In this session, I will be using PyroSim, a software for fire simulation, to demonstrate the topics. I would also like to express my gratitude to Thunderhead Engineering for providing the academic license for this software, enabling us to explore fire scenarios in a realistic and interactive manner. We will explore about PyroSim, the fundamentals, and we will demonstrate a fire model example and getting and viewing output, how to insert materials, and some more explanation. Why we need PyroSim? PyroSim is a software which uses FDS to model the dynamics of combustion. The problem with FDS is that it is text based with photon name list syntax, and it also needs smoke view for visualization. But Pyrosim can import CAD models, and it has inbuilt smoke view viewer and many more advanced features. And it also creates the FDS record with correct syntax. In summary, Pyrosim is the graphical user interface we interact with, and FDS is the underlying simulator that is calculating. The process of fire simulation in Pyrosim goes like this. First, we will create the geometry and insert the properties, define the combustion reaction, including fuels and reaction, and do the simulation using mesh, boundary conditions, and some simulation parameters. And we can get the output using devices such as basic data output, we will explore later, sprinkler, smoke detector, etc. And we will also see about fire scenarios and some simulation parameters like wind and devices, etc. Now let us see how the interface of Pyrosim looks like and what are all the components. So friends, this is the graphical user interface of Pyrosim looks like, and here we can see the menu bar, and these top two bars are called view toolbars, and to the left it is a modeling toolbar, and this is the navigation view, and the gray color panel you see is the model view where our model will be shown, and at the bottom you can see different tabs are available. This is called model view tabs. As I have told you earlier, the fire simulation process starts with defining the geometry, then the properties, and then the combustion. So let us create a geometry from Pyrosim itself. If you have a pre-built geometry in AutoCAD or any other 3D modeling software, you can import them into this Pyrosim using import fds/CAD file. You have to save your 3D model as .dwg file, and you can import the model into Pyrosim easily. But now we will create a geometry inside this Pyrosim itself. Let us start creating the geometry. I am going to 2D view tab and make sure to select the show reset to top view, and now I can see from the view cube XY plane is activated. So I am checking the grid spacing and it is in 1 meters. I want to change this to 0.2 meters and I am clicking on that. Okay, now I want to select slab abstraction and you can click, and I am creating a 6 meters by 6 meters slab. Just click on the origin point and it will be closed. You can see the slab has been created. I am renaming this as floor. I want one more slab like this with a 3-meter height for a roof. So I am right clicking and selecting move, copy, number of items 1, and in the Z direction I am giving 3 meters. So my roof slab is also created. I can rename this also. And I want wall enclosed on all 4 sides. So for now I am hiding this roof. Just hide and go to 2D view. Make sure you are in the top view, and here select the draw wall obstruction click on this, and while this tool is activated, right click on that and select tool properties. You can see the wall starts at z equal to 0 and the height of the wall is 2.75, but we have given 3 meters height, so I am changing this to 3, and wall thickness I want to maintain as 0.2 meters as it is, and click OK. Start drawing your wall. So second click, and you can continue until you click on the finish. It will not be finished. So since this is an enclosed surface, now if I give show, you can see the block model. Again I am hiding the roof just for simplicity. I want a simple partition inside this room, so I am again selecting a wall obstruction, and just randomly I am giving the obstruction at around 3 meters. So in this point I am starting, and I am giving distance of 3.2 meters, and you can see here, since it is not a closed wall, it will extend like this. So right click and give finish. If you give close, then it will become a triangular wall. So click on finish. So the partition has been created. We will see in the 3D view. Next, we will create doors and windows. For that, in the model, you can see draw a slab hole, wall hole, and a block hole. Since we want a door, we are choosing draw a wall hole. Select on this. Again, when the tool is selected, right click and go to tool properties to check whether the Z location starts from 0 and the height of the hole is now only 1 meter, but I want to give 2.4 meters, and wall thickness is 0.2, same. Now I am selecting a door here. Just click on any one corner, and you can see I am giving distance 1.2. Right click, finish. But the hole has been extruded in the inside. Now I want to change it to the outside. So you can simply right click, go to properties, check the geometry, and the alignment is on the left side. You can see it says alignment on left. And if you click on right and click on OK, then it will be correct. And I want one more door inside this small partition. Again I am selecting draw a wall hole, and here I am giving the same. Click and finish. Here also you can select the alignment. If it is wrong, you can change this. And I want to create one window here and here, this side. So now I am going to select again draw a wall hole, and I am changing the tool properties. Now my Z location starts from 1.5 meters and the total height is only 1 meter. Click on OK, and I am drawing a window here. So for a clearer view, I am selecting a big dimension. According to your model, you can give. And again I am selecting the wall hole, and whatever properties I have set for the previous tool, it will be maintained. So I am again selecting this and applying a small window, give finish. Now let us view this in the 3D view. So you can see one door here, one window, and one small window, and one door. And the roof is there. If I click on show, the inside objects will not be visible. You can rename all of these components so that it becomes easier for our further analysis. We have completed the geometry definition. I want to add one more block to define the fire source. So now I am again hiding this roof and going into 2D view. Inside this room, I am going to draw a block abstraction. So select block abstraction. You can see it is already predefined with some properties. So I am changing them. The Z location is 0, height is 2.75 meters. I don't want that much, so I am making it as 0.2 and 1 meter by 1 meter cube. Or you can just click on this and right click, go to properties, select the geometry. You can see minimum, maximum coordinate sizes of all the axes are mentioned here. So I'm going to roughly estimate here from minimum x 1.8 to I'm changing this to 1, and minimum y direction is the height, and here it is 5 to 5.2, so I am changing this to 4 to 5, and z is the same. So I want to check this in this 3D view. So here the block is there. So consider this as the fire source, and on top of this we are going to define the fire reaction. To define fire, there are two different components essential. One is the reaction, which is chemical, and other is the surface, which is physical. So you have to have one reaction and a surface to start simulating fire. So the reaction is the main parameter that governs the combustion, and more than one reaction also is possible in pyrosim. And the surface, we have selected this surface, top surface, and this is a physical characteristic of a solid or even an opening, just like a vent. And there are various types of surfaces available. So first let us add the reaction. Go to model menu, edit reactions. Here there are two options available. One is a new user defined reaction, but for now I am going to use add from library. There are many reactions already available, and now we can choose the SFPE polyurethane reaction. Select this from the library and click on this to load it to the current model. Click on close. All its properties will be written inside our model. You can click OK. To verify that, go to the record view, and here the reaction has been already added. You can see the reaction ID and from where it is taken, what is the fuel, CO yield, soot yield, and heat of combustion, all those properties. If you have a specific fuel which is not listed in the FDS library, you can input those from this option called new. So here you can create your own chemical reaction, and on which basis you are creating, all those are there. You can just explore these options. So now click on OK. You can see from the side navigation view in the reactions, the reaction has been added. Now we need a surface for that reaction. So let us create a fire surface. Go to model, edit surfaces. Now I am going to create a new surface, and I am calling this as fire surface, which is a burner surface. Click on OK, and you can see the heat release rate per area, HRR-PUA, is the input. You can get this value from various standard guidelines and experiments or previously published literature article. But now for demonstration, I am just taking this as 500 kilowatt per meter square. I am clicking on OK. So I have created a reaction and a surface. Now I need to define this surface onto the block, and I am clicking on the block, right click, go to properties, select the surfaces tab. Instead of single, select the multiple. Here you can see in the Z direction the top surface is, so maximum Z I am changing it to fire surface. So click on OK. You can see this has been changed color, which means the fire surface we have defined has been applied only on the top surface of this block. Now let us create the mesh for this analysis. Again go to model. Here you can see edit meshes. Click on new and give a name. For now mesh 1 is enough. Click on OK. You can see it has already predefined some mesh, but the dimensions, the starting and ending boundary of the mesh is not as per my liking. So I will change this. I want some spacing all around the model to allow the wind fluctuation. So I am keeping minimum X as 0 only, and maximum X is 8, and minimum Y, I'm just checking which direction is in Y. Minimum Y is maybe minus 0.5 and maximum is 6.5. And here on top I am allowing some 3.5 meters extra, and I can change the number of cells in all X, Y, Z directions, or I can straight away go here and change the cell size. You can click on it, just give 0.2. You have to make sure that all of these mesh checks have been showing us green color. So here in the top you can see mesh alignment test has been passed. So click on OK. You can see, okay, so in the X direction there is space is more, so I want to change this. If you want to change this, again go to mesh, double click on that, again the same window will be appearing. So you can minus 0.5 and here 6.5 I am giving. Click on apply. Yes, this is perfect. So let me check. Mesh has been defined, and further more options are available. So here you can see mesh boundary, split mesh, partition and refine mesh all are available. So you can just play with these options. And now I am going to keep open mesh boundaries on all the 4 sides except for top and bottom. So bottom surface mesh vent and top surface I am deleting. The blue color which shown here means that it is a open mesh, open boundary which has an interaction with the ambient condition. But this yellow color here shows that it is closed. This is just to show you the possibility. According to your environmental conditions of the model, you can change the surfaces to open or closed. Now we have defined the reaction, the surface and the mesh, and now we have defined the boundary condition also as open. Now we have to input the simulation parameters. Going here, analysis, simulation parameter, start time is 0 seconds, end time is written as some 1 power minus 3 like that. And now I want to change this to say 1 minute. Just for a demonstration I am keeping this. You can change this according to your values. Click on OK. Now our mesh is ready. model is ready. Now you can save the model into any of these folders. I am giving us fire model. It will be saved as .psm file. Now we are going to run the simulation by clicking on this run FDS. You can run FDS or run FDS parallel or FDS cluster if you have the HPCE configurations. For now I am just clicking on run FDS. The FDS started running. It will show us any error was there in the configuration. So it is running fine. The total simulation time we have defined is 60 seconds and now it is running in 2.6 seconds. Let me resume when it completes 60 seconds. Depending on the system configuration, it may take different time to complete your simulation, and you can see the simulation has been completed successfully and it will automatically show the results. And carefully observe that this is .smv file, which is the smoke view file just for visualization. And in the right side navigation you have different options. I have enabled the 3D smoke option. So if you want to enable, double click, disable, again double click. I want to check the fire growth. So I am rotating the model for my view, keeping it. And in the bottom you can see play, stop, all the menu buttons are there. You can click on play. So the flame propagation and smoke spread has been recorded. You can see through the openings how smoke is escaping to the outside. And you can also see how smoke is getting clouded on top of the room because we have given the top mesh boundary as closed and all the other 4 sides as open. The smoke has been trapped here in the top. So this is how you can use a model to study the flame growth and smoke spread. Now let us see some more output which we can get from this pyrosim. I am stopping and closing this window. If you want to save this current position, you can click on save and you can close this fire simulation also. Keep only this PSM model open. And now let us explore the different data output available. So the first one is devices. You can access devices through the through the devices menu, and you can see new gas phase device and new solid phase device and thermocouple, FED, heat release rate device, heat detector, smoke detector, sprinkler, nozzle, etc. In this demo, let us see what is gas phase device, solid phase device and a smoke detector. So gas phase device means that it measures the quantity in a gaseous cell from the center of the cell, and solid phase device means it measures in a solid cell from the face of the cell. So to measure wall temperatures we can use solid phase device. And smoke detector, here it measures different parameters that we will see. To start defining the devices, I have clicked on devices menu, devices, and click on new gas phase device. You will see this window and you can rename your device. I am saving it as temperature 1. You just give some meaningful name, and the quantity which I want to measure is temperature. So I am scrolling down, searching and getting the temperature. Here temperature is available. And the location where I want, I can click here, or you can click and edit later in the model itself. This is one way of defining a gas phase device. Other thing is, one more method by which I can define the devices is, for example, I want to measure the temperature in this window opening. So this is actually a hole. So inside this passage, I want to measure the temperature. So I am going here in the model view and selecting draw a device. Click on that, and if you come here and right click, select tool properties, you can see this is just named as device. I am changing this to temperature window, and Z location you can change later, and device type is gas phase device, and the quantity I want to measure is temperature. So I am clicking on OK, and here I am just clicking here. Since we did not modify the height of the device, it is inside the wall. Now I want to change this. For a better view, I am going to 2D view. From the top, it is placed here, so I want to move it little bit further in the -x direction. So I am double clicking on that, and in the location it is as 0.2, and I can give 0.1. For now I am keeping that, and it is inside. And now I am going to select any of these side views. So I want this up here inside the window hole. So I am increasing the height in the Z direction. So I am again right clicking on that, go to properties, change the height. So instead of Z 1.375, I am giving 2. You can see from this side view as well as in the top view, make sure that the defined device is inside one of the mesh cells. So you can check with different views to make sure that it is inside. So we have defined one gas phase, and I want to place one solid phase device just above the fire source but on the ceiling to measure the temperature. For that, again I am going to devices menu, selecting a new solid phase device, or just like we did earlier, you can click on the draw a device toolbar, select, and you can right click, select on tool properties. Now change this to solid phase device, and instead of temperature window I am giving ceiling temperature or roof temperature. And here we can change this Y location later. Device type is solid phase, quantity is adiabatic surface temperature. Instead of adiabatic surface temperature, you can change this to wall temperature. You can see if we change the device type to solid phase device or some other device, the output quantity is also varying based on the device type we have selected. So now we want wall temperature. Please make sure to select wall temperature and click on OK. So now you can place your device just above, and remember this solid phase device will work on the surface, the face of the mesh element. So I am clicking on here. I am just checking in the 3D view where it is actually placed. The height is correct, but the coordinates x and y are changed. So I want to change this. So I am right clicking, changing the properties. In the y direction, I want to increase the distance. So I am just trying 2.5. Let's see. It is moved a little bit. So for a clear view, I am selecting the top view in the 2D view. So here is the solid phase device. So I want to move this from here to here. You can click and drag if your cursor allows that. Here you can click and drag. So from the top view it is located correctly. I am checking other views also. For example, this front view. In the front view it is on the wall surface only. And side view, here also it is on the wall surface. Now I want to add one more smoke detector. I am again going to the top view. I will select draw a device. Right click, select tool properties. I am changing this to smoke detector 1. And here smoke detector. And the Z location I am changing to 2.9. Device type is smoke detector, and leave all the other options as default. So appropriately you can place your smoke detector. I want to check the other views. So smoke detector is placed here, which is fine for now. This is all for demonstration purpose. You can change all these devices according to your research model. Now let us see the other types of output which are available. So one of the important output which we get from the fire simulation is 2D and 3D slices. You can see in the output 2D and 3D slices are available. I am going to define 2D slices. Here you can give a name. Now I am giving temperature 1. In the XYZ plane, I can select X plane, and the plane value is I want this plane to cross across the fuel source. So I am approximately giving 1 meter. What is the quantity I want to measure? And please note that this is a gas phase quantity, not a solid phase quantity. So it is measured inside the cell. And I am selecting temperature. Use vectors. You can give yes or no. For now I am giving no. Cell centered is also no. And I am adding one more row. And here also I am checking what is the temperature range near the ceiling. I want to view this in a 2D slice. So I am selecting Z plane. Change this plane value to 3 meters. And here also I am giving the same temperature quantity and the same. I am adding one more. Here I want to check the visibility along the same plane as where my door is placed. See here, from this place along the Y, I want to check the visibility. So I am selecting Y plane, and I am giving this as 0.5. And here you can see select visibility, use vectors. You can give yes and cell center yes. So now in this model you can see there are light pink color planes defined. This shows that we have defined the 2D slices. Likewise, you can try with 3D slice also. For now I am leaving it up to you. And now again we are running the same simulation, and we will see what are all the input data output devices we gave is working or not. Again I am clicking on run FDS. If it says override output, in this case I know that I can overwrite my output, but please be sure to save your model as a new file before overwriting the output. So I am giving yes here, and let me wait for the model to complete, and will be. So here I am encountering some error. So let me see what is it. In this SMB model view, it is not showing me anything. It will not because of the error. So I am just closing this. and we'll see error 4 to 7. Device ceiling temperature requires repositioning. So this ceiling temperature we have placed at certain coordinate and FDS is not compatible with that. So I need to change the position of ceiling temperature. So let us debug that. We will go into the devices. Here in the navigation you can see ceiling temperature. In order to view that, I am going to 2D. Sorry, we forgot that we have a roof. I have given the coordinates of ceiling temperature on top of this and asked FDS to measure the wall temperature. So which is wrong. So I am dragging it down to keep it near the bottom, which is just above the fire source but at the bottom of this roof slab. Now let us see whether this simulation runs. I am saving the file, giving run FDS again, overwriting. If it has further errors, it will show. Okay, now the setup was proper, so it started running. Now let me complete this simulation. The simulation is completed. Now we are viewing the smoke view file. So let me just clear all of these results. So this will be the model. You can change the view by going here. Now I have chosen wireframe rendering for simplification. You can also keep in any of these other if you want. And now let us see the results we have obtained. We have already seen the 3D smoke, which is the fire growth, and smoke, which is soot density. But I am now interested in seeing the outputs of visibility and temperature, which I have defined as a 2D slice. You can see, first I am selecting the temperature 1 slice. Just double click on that, it will be shown. So we have already discussed that the slices will be showing only the gas phase quantities, not the solid phase. So the walls and the block has not been read out from the output, and you can see the legend shows that the maximum temperature is 370 degrees Celsius. If you want to see the growth, you can just click on play and it will be shown. Likewise, you can examine other slices also. I am disabling this and enabling ceiling temperature. So since I have chosen the height of 3 meters, it has not taken any of the slab temperature, only the gas phase quantity. It may not show much results, but let us see how the temperature change is happening when there is a opening. You can clearly see the temperature increases just outside this window, and there is the small window. Like this, you can have many number of 2D slices and 3D slices to examine the output quantities which are of your interest for your research. And we have defined one more, which is the visibility. I am clicking on here. You can see the legend says that the blue color is 0 and red is 30. It is just the visibility plane. So if it is red, which means that the visibility is up to 30 meters. So if I click on play, you can see as the smoke density increases, there will be a change in visibility. Wherever the smoke is clouding the view, there the values are changing. This is particularly useful when you are designing for any evacuation plans. Now let us also see the output we got from the devices. I am disabling this. I am minimizing all of this. You can see here only 3D smoke, 2D slices, and no more device outputs. So for that you need to go to XY plot data, right click, load CSV file, and whatever the results we have stored is already made as a CSV file and it is put into the same folder, named folder inside near the model. So here I want the device data. So DEVC is device data. Click on OK. Open this one. You can see there is a downward arrow. So I'm just double clicking on temperature window. As you can see, the temperature window is measured from a gas phase device, and I am again double clicking on ceiling temperature. The ceiling temperature has not changed from 20 degrees C, which is the ambient temperature, which is already predefined. We will just see why this is happening. Yes, I am closing this. I am clicking on smoke detector, and smoke detector also did not detect any of the percentage of smoke. We will debug this. Since the solid phase and gas phase smoke detector devices are sensitive to the mesh, the problem may be because of mesh sizing. I am just closing this SMD, closing this one, and if I change the coordinates of this ceiling temperature and smoke detector is actually placed inside this slab. So if we drag it down, it may give results. So I have changed the coordinates of these two devices, which is ceiling temperature and smoke detector. Let me show you in 2D view. So we have seen about gas phase and solid phase devices. This is the problem with the definition of gas phase and solid phase. Let us see a little bit about gas phase and solid phase. So take for example, this is the mesh element and you are defining a gas phase device. Means the device should be placed inside the mesh cell boundary. It can be here, here or here, anywhere, but not on the boundary. If it is on the boundary of the mesh cell, it will not give you any results. So wherever you place inside the cell, the device is going to measure the output quantity from the center of the cell. But in a solid phase device, you have to place the device on the mesh boundary, means the cell element boundary. So like this, if you place it inside the cell, it will not generate any results and it will show you the ambient conditions only. So likewise, while defining a solid phase and gas phase device, you have to really make sure that you are placing in the correct coordinates. So here we have placed a solid phase device for ceiling temperature and smoke detector is a gas phase device. So I have changed the coordinates in such a way that the ceiling temperature, you can see here, it is lying on the cell boundary, and smoke detector, I have already told you that smoke detector is a gas phase device, so it should be placed inside the cell. So now I have run the simulation again and let us view the results. So if you have completed simulation, and you can go here, view results. Now since I have already loaded the CSV file, it is showing here. Otherwise you have to again go to XY plot data, right click, load CSV file, locate the model folder, and you can click on the device CSV file. So you can see temperature at window exit is showing me results, and ceiling temperature, it is still not getting any temperature reading. We will see why it is happening. And smoke detector, you can see from first few seconds, about 3 seconds, it is not detecting any smoke, but after that the smoke percentage started increasing and after certain time like 4 seconds, the smoke percentage has reached its 100% volume. So like this, you can change the coordinates of gas phase and solid phase devices to make sure that you have placed it correctly. And the problem with sealing temperature is we have defined only the model and we did not give any material for the geometry. So in this case, we can just select what is the material which is assigned. So you can see, go to surfaces and the surface is default. For pyrosim, the default surface is inert surface, and inert surface has no specific material properties, but it allows heat transfer. So that is why on the surface of the slab there is no rise in temperature and it is only showing the ambient temperature. Now let us see how to apply materials, and let's see if the sealing temperature is getting detected after material application. So to define materials, you can load it from library or you can create a custom material also. For loading from library, you have to go to this option. So here in the model menu, edit materials option is available. Click on that. So there are two options, new and add from library. New is useful when you are defining your own material. You can click on new and you can follow the on-screen instructions. For now, I am going to add a material from library. So add from library. Here in the right side, I am seeing all the preloaded properties library of FDS. So for example, I am selecting concrete. You can click on this arrow to make it to current model. Click on close. All the properties are available here. So all these properties are taken from a reference and which is mentioned here in the description. You can click on OK. So whatever material, reaction or particle you are defining inside pyrosim has to be applied on a surface. So we have to create a surface for this concrete, just like we have created a fire surface. So again, go to model menu, edit surfaces. Now I am going to create a new surface. I am calling it as concrete 1, and this is the surface type is a layered surface. Click OK, and here in the material layer tab, it is asking the thickness, material composition. So thickness we have to give, the thickness is 0.1, and material composition you can go to edit, and in this I am not layering any material on top of concrete, so I am just giving complete 1 and selecting the material concrete. I am clicking on OK. So now I have created a surface called concrete. Now I can select all the surfaces, walls, and apply this. I can select here also. I am selecting, by clicking control, I am selecting this elements. So except this, I am selecting all, right click and go to properties, surfaces. In single, I am clicking on concrete. You can see the surface color has been changed. Let us view in realistic with outlines. So you can see earlier the surface color was yellow, which was showing that it is an inert surface. So see here in the definition of surfaces, inert surface and concrete are there. Now since we have applied concrete surface, it has been changed from yellow to this light green color. Likewise, you can create your own material library also. Now let us run the simulation once again and check whether the sealing temperature has detected any temperature value. I am clicking on run FDS, overwriting the output. The simulation has been started. Let me resume after the simulation completes. The simulation completed successfully and I am going to view the results. Let us check whether the sealing temperature, yes, you can see here now, since we have changed the material surface from inert surface to concrete surface, based on the thermal properties of concrete, the wall temperature is detected using this device. So there is no change in smoke detector. Now let us look into some of fire protection devices which are available inside PyroSim. So there are many fire protection devices available, such as sprinkler and smoke detector we have already seen, and we can connect alarms to that to properly plan an evacuation plan, and ventilation systems and other controls. Let us see one by one. First, let us look into how to place the sprinkler. I am changing this model to wireframe again. In the devices menu, if you click on that, there is a new sprinkler. Click on new sprinkler and it will show you the dialog box. So here, if you know the coordinates of your sprinkler, you can just start filling in them. Otherwise, in this model menu also, click on draw a device, right click, select the tool properties, change the device type to sprinkler. So in this, you can edit, and as you can see, there is spray model, generic commercial spray. There are many other varieties also. For now, I am just leaving it as generic commercial spray. You can change these parameters as per your research model and click on OK. You can place the sprinkler at the desired location. So let me go to 2D view. I am viewing from top and I want sprinkler at 2 different locations. For example, I am just checking that the device type is sprinkler, clicking on OK. So I want to place the sprinkler near this location and somewhat far away, just to check its activation time. I am clicking on here. So you can change the names here as well. So I am renaming this as sprinkler 1. And sprinkler 2. Now let us view where it is placed. I can go to front view and I'm just seeing, okay, the height is not at a desired position. So I am increasing the Z coordinates. We have already given 3 meters height. So I am just giving 3 meters height and checking whether it is placed. Okay, it is going above. I don't want that. So let me reduce this to 2.8 meters. So now my sprinkler is here. Likewise, I am changing the height of this sprinkler also. 2.8 meters. Click on OK. This is how you place sprinklers inside the model. You can follow the specific guidelines given by any handbook or codal provision for your research models. The next type of fire protection available is fire protection surfaces. Fire protection coatings are nothing but the insulation protection given as a coating on top of the construction material. So here we can see that in our materials library, we are going to add from library. So you can see gypsum and some insulation material are available. You can select this and create a new layered surface and create a multiple layer of surfaces, and you can check whether the temperature variation is there for the applied multi-layer protected surface. There is one more fire protection method available inside PyroSim which is very useful, and that is called vents. So to add a vent, you have to go to again model surface, model menu, click on edit surfaces. Here we are creating a new surface which is a vent surface, and surface type is exhaust. You have to specify the volume of flow. For example, here I am giving 10 meter cube per second. So this value is just an example. You can change this value according to the codal provisions or handbooks published. So click on OK. Here the vent surface has been created, and in any of the wall I can create a vent. So I am going to 2D view and say for example I am selecting this side. So let me just check which side is appropriate for providing a vent. I am hiding the roof to check. Okay, my fire source is here. So I want to give a vent, an exhaust in this side of the wall, so which is XZ plane. So I'm going to 2D view, select the front view. So XZ is there. Select the back side. I'm just checking. Change the view. Okay, I can give here again to wireframe model. Now I want to create an exhaust vent here. You can see here there is an option called draw a vent. I'm clicking on that and I am start drawing. Just click drag and release. Let me just check on which side this vent is applied. Okay, it is on the opposite side. I can change the dimensions from this side to that side. I know the size of this room, or if you don't know also you can measure from this tool, measure. So click on this location and this, you can see the total distance is mentioned here as 6 meters. Clicking escape. So here double click on vent properties, go to geometry and in the y direction. So the plane is in y equal to 0. Now I want y equal to 6 meters. Let me just check whether it has been applied. Okay, so it has been applied properly. Now in this vent I am selecting the surface as vent surface because I have defined a surface as exhaust, created a vent surface already, and I am taking that and applying it here. So basically whatever you are introducing into pyrosim model, that has to go into the geometry using surface option only. So click OK, and our vent is always on. Currently the activation is always on, but I don't want the exhaust to work all the time. So I am going to introduce a control by saying that when the smoke detector is activated, when the smoke detector is detecting 100% of smoke, then the exhaust has to be open and the air should be sucked out. So for that I have to define a control logic. I can do this by going to control. So here let me just check with that. So in devices menu you can see edit activation control. Click on edit activation control, click on new control, give some name. Now I am giving exhaust control. Control type is activation. So there are other options also. Click on OK. So the input type is a detector. I am taking the data from a detector and this control is to be activated. So you please read this sentence. Activate nothing when nothing activates. So all these blue color underlined words are hyperlinks. So click on nothing. You can see all the components inside our pyrosim model. So now I am going to search for smoke detector. Select smoke detector. Click on OK. Sorry, I have to select the exhaust vent. Okay, now it changed to activate. Activate smoke detector vent. Sorry, smoke detector I can clear. Activate the vent when the smoke detector activates. So here only the devices are shown. So select on smoke detector 1, it activates. You can delay the activation by 0.0 seconds. So for example, now I am giving, say after the smoke detector activates, I am giving some 5 seconds or 10 seconds delay. So let me give 5 seconds for example. Clicking on OK. Now it has been applied successfully. Now let us run the simulation and check whether all the protection methods we have applied are working properly. I have extended the simulation up to 60 seconds and the simulation has been completed. Let us just check the results. We have defined sprinkler and other devices here. So I'm clicking on the device data. First 3 are already defined and we are just checking at sprinkler 1 and 2. Double click on sprinkler. You can see from the ambient temperature, the temperature has been rising and then suddenly it is dropping. It clearly shows that at this point, around 40 seconds, the sprinkler 1 has been activated and thereby the reduction in temperature is observed. So likewise, let's check sprinkler 2. Here there is no drop in temperature, but you can see the temperature value has not exceeded 35 degrees Celsius and there is a predefined temperature associated with every type of sprinkler, and in this type of sprinkler we have defined the minimum temperature to activate the sprinkler has not been reached yet. So the sprinkler 2 is somewhere around here from the farthest corner to the fuel source, but sprinkler 1 is placed near the fire source. So this is activated and sprinkler 2 is not activated, which confirms that sprinklers are working properly. Now let us visualize how the sprinkler is working. For that you can turn on the particles, and for simplicity I am just turning on HRR PUV, not soot density. So if I turn on soot density, it will be clouded with smoke and water particles may not be visible. I am clicking on play. So there is this, the fire growth is not clearly seen. Let us enable some temperature slice. Okay, so now for visualization I have enabled this. Now I am clicking on play. You can fast forward this using increase speed. You can check at which time the sprinkler gets activated. It is around 41. So here in this box you can select a specific time. 40 seconds the sprinkler is not turned on. 40.5 not turned on. 41, yes, it is started. But until the end of this slice, sprinkler 2 has not been activated. So you can clearly see that the sprinkler pours water and it controls the temperature rise. And we have also defined the exhaust control. Let me change this to realistic with outlines. So here is the exhaust. So now let us replay this again to check. So at the starting, when time equal to 0, there is no exhaust vent. You can see when we hit on play, we have given a control of activate the exhaust when smoke detector activates and delay the activation by 5 seconds. So now here the exhaust vent has been activated. You can check this in this visual manner also. And one more way to check whether the exhaust control has been activated is by going to XY plot data, right click and load CSV file. Here you can see there is a control.csv file. Click open, click OK. So whatever the control activation we have defined earlier will be shown here. We have defined only one exhaust control. Double click on that. Here you can see from the earliest time for a few seconds until 8.22 seconds, the status of the exhaust control is -1, which means it is turned off. So at 8.22 it is activated and which is showing the status of 1. So -1 means it is turned off, +1 means it is turned on. So likewise, you can examine all the other control devices and fire protection methods. So friends, we have looked into the essential aspects of fire simulation, including the geometry creation and adding fuel reaction, material properties, and some fire protection methods. These are just the building blocks for accurate fire resistant design. Here are some of the parametric studies which you can carry out. Try to change different surfaces, take 2 or more surface types and try to compare the results, and compare the output of different devices, gas phase and solid phase, and why the 2D slice and device output are different. Just check different reactions, define different reactions using the FDS library and try to compare the results for different fuel reactions. And you can explore these parametric studies with a fire scenario option. To extend this fire simulation to fire resistant analysis and design, you can integrate structural elements and apply fire exposure scenarios to assess how materials degrade under high temperature. In order to do the subsequent steps, you have to couple the thermal and structural analysis. So first, fire simulation, take the output time temperature curve HRR data to get the fire resistance rating and thereby design for fire protection. The subsequent methods cannot be performed within FDS or PyroSim, which is CFD based essentially. In order to do that, you can use some other tools like ANSYS, Abacus, or any suitable tool. For more details, I recommend the following reference textbooks. We would like to acknowledge the academic license which is provided by Thunderhead Engineering for the use of PyroSim. Here are useful textbooks: Fire Resistant Design of Structures, Design Aids of Offshore Structures, Design Aids of Offshore Topside Platforms Under Special Loads, and Advanced Steel Design of Structures. Some additional resources include the tutorials and user manual by Thunderhead Engineering, FDS User Guide, and SFPE Handbook of Fire Protection Engineering. Thank you.